So yeah, my name's Sam Whiteley. Data platform MVP. I do lots of Microsofty type big data things. I spend most of my time playing around with lakes and building data lakes for people and doing consultancy around that kind of stuff. So that's kind of me. And I kind of used to be very much kind of traditional data space, building databases and data warehouses and doing all that kind of Kimball, big fan of Kimball. And then kind of I started doing lots more stuff in the cloud. And obviously kind of just like the guys were saying, you start to struggle. Starts to struggle getting all that data into a database and trying to get that stuff to actually work properly. And it gets harder and harder and harder. And a long time ago, I adopted Spark. So for the past few years, I've been essentially still an analytics, warehousing, business intelligence kind of trying to do analytics on data, right? Except essentially doing it with Spark and a whole range of tools around that and that ecosystem. So kind of what I want to do is give a real like high level, super entry level. This is what Spark is. This is kind of why it means a lot to me. This is why I've chosen to kind of like pivot away from doing a lot of stuff in relational databases and pretty much do everything in Spark these days. And then kind of how it fits into the open source community, how it kind of all the different components and how you can get involved and how you can help out. That's kind of the plan. So got some slides. I'll kind of whip through and give you a little potted history of kind of where Spark came from, kind of how it grew, how it relates to all kind of stuff. That's the plan. So a long time ago, back in the days of yore, Google released the Google File System papers. So it's essentially back when they were trying to index the internet and trying to actually just how do we process reams and reams and reams of text data and actually pull stuff, actually any kind of information out of it. And they struggled to get that on single disks. And so just like the guys were saying with sharding and the idea of saying, I need to take my data and split it out and distribute it and do all that kind of stuff. That's essentially what they did. And that's been adopted by a whole load of tools and technologies these days. So you see things like HDFS, the Hadoop distributed file system, which is taking that kind of thing. So these days in Azure or in AWS or Google, lots of their storage mechanisms are taking these ideas. So we say, I've got a CSV, I've got a flat file, I've just got some data sitting in a file. And actually, rather than just treating it as a single file, most of these tools will just automatically split it up and say, well, I'm not going to just deal with one file, I'm going to deal with several different chunks of those files, and then take those chunks of files and just put it on lots of different disks. So I'll always have at least 3 copies of any individual chunk of a file. And so you have like this data replication and spreading out over super, super cheap disks. And so it's the whole idea of saying, I want to get speed and I don't want to buy a really, really expensive, super fast, whizzy server. I just want to just make lots of copies of it so I can use parallelism to make things go faster. So they did that with a load of data, and that was kind of that's like the modern evolution of what was came from GFS, those Google File System papers. And then they were like, well, we've distributed all our data, but we need to be able to process that data. How do we still just have one server reading a load of distribution, and that doesn't make any sense. So the thing called MapReduce kind of evolved and kind of came from a similar group. And that's an idea of saying, how do we take like a compute job? How do I take like a task? I want to go and sum a lot of things. I want to count individual words. I want to go and do some kind of analytical query, but I want to spread it across a load of cheap computers rather than have this one big expensive server. So you have this kind of thing. Again, Google trying to index the internet. You've got a giant bit of text. And actually we can take that and we'll just split it up similar to how we're splitting up those CSVs and go, well, actually I can treat different chunks of data. And then we can take that and say, well, I want to reorganize that and I want to map it. So I want to change that rather than just a one big block of a column. I want to actually say, well, this is the word and this is a count or a kind of, an incrementer next to it. So we're taking something that was unstructured, just a pile of words, and we're changing that to actually be shaped like a data set. And suddenly we're seeing it become more of a managed thing from this giant blob of data. And then we can actually rearrange it. Well, let's actually, rather than keep it as those original sentences, let's just group all these same words together. And then we can actually run an aggregator over it. And basically, each one of those blocks, each one of those chunks is a bit of compute that we can actually kind of give to different servers. And suddenly we're taking this one idea of saying, I've got a query that I need to run. And now we're saying, I've got lots of different distributed queries, which are each running on their own little chunk of the data, but that actually is part of a whole process. And that's kind of the idea. Now, that eventually became, part of the Apache Hadoop ecosystem, and this just evolved and grown, and there's so many things in there. So you can go and look at things like Pig, you've got Hive, which is very, very important. Just essentially, it's a massive ecosystem of its own. So that was kind of like the granddaddy, the grandfather of lots of the modern big data tools that we're using. Now, one of the problems with that is each one of those like chunks of work is essentially reading data, doing something and putting the data down again, and just constantly reading back and forwards and back and forwards. And that's not always that fast, even though we're doing it in parallel. So this chap, Matteo Zaharia, came along with a load of colleagues at UC Berkeley, and they invented this thing called Spark. They kind of came up with the Spark project. Now, that's essentially saying, I want to do the same thing. I want to take this idea of lots of distributed bits of compute, but why don't we just do it in memory? And why don't we actually, rather than just doing each thing, put it down again, actually just work out the most efficient way to do a load of things at once? And that's really all Spark kind of is. It's big data style MapReduce, but evolved slightly and done in memory. We've still got the same idea of separation of storage and compute. So you're putting all your data down on really cheap, essentially in a lake, and then you're spinning a bit of compute, doing a load of work in memory, and then closing it down again. Now, they took that and they went and actually sort of pushed it out as the Apache kind of Spark project, and it became an open source project. And then those guys actually went and started a company called Databricks, and so you're seeing Databricks as a service everywhere, because what do if you invent something really cool and you open source it? You make a company that sells it and makes it easy to use. So you'll see Databricks around. We'll be using Databricks for some of the quick demos. But essentially, it's a flavor of Spark. It is a managed version of Spark that you can go and see. So that's kind of what Spark is in a nutshell, kind of big data, but in memory and made slightly easier. It doesn't give you that much. To put it a little bit more in context, you end up with this kind of thing. So essentially, we're talking about clusters. And so we're talking about a big parallel cluster, which has a driver. So it has kind of some kind of head node, some kind of compute that's receiving your query and deciding what to do. And then you've got a number of workers. So that's the grunt. That's the thing actually doing the work. And that is entirely flexible. It can go anywhere from 2 workers, the minimum level of parallelism, all the way up to hundreds, thousands, whatever. So you can actually have a vast amount of scalability here. And because the data's not actually stored on the cluster, you can turn it all off. You can turn it on, run it over data, spin it down again. So it's very much kind of very flexible, very scalable. So you see this kind of thing. So we'll write a bit of Python or Scala or R or SQL, basically our language of choice, throw that at the driver. The driver decides, actually, how parallel am I going to make it? How many chunks of work do I need to do? Pushes it down to the workers. The workers then go and get their individual bits of data. So each one is just reading only the data it needs from one of those many parallel disks and going down and kind of sucking things back up again. Pulls up, puts it in memory. Again, it can then do a load of tasks in memory. And there might be several steps here. So we might do some work and then aggregate all the data onto another worker, do some more work, do some things, pushing things around. And then eventually return my results back to me, and I get to go and see what it looks like. So you see that kind of parallel steps, but that's kind of all done for you. Essentially, almost everything you do in Spark is doing that kind of action. Tell the driver to do something, the driver figures out how much parallelism it needs, pushes stuff down to the workers actually do a load of stuff, and then give you results back. Or maybe it doesn't even send it to the driver, it just goes and writes it down into the disk. So loads and loads and loads of different stuff. Okay, so what do we actually use it for? Yes, it's a good big data querying engine and all that stuff, but it doesn't really tell you how useful it is. So one of the biggest things for me is I use it for ETL. So I used to be using things like SSIS and Talend and kind of just traditional ETL tools, which is pushing data across. But these days, I just tend to do everything in Spark, and the quick demo I'll show you kind of shows you why that is. But essentially, taking data from a source, transforming it, calculations, you're cleaning it up, validating the data, maybe shaping it into facts and dimensions. If I'm doing a Kimball-style warehouse, I can use Spark to actually do that whole journey, which is great. But it's very, very flexible because it can also take in JSON. It can take in a stream. I can do live streaming via Spark. I can take in geospatial data. You can use it to solve the hardest problem in data science because it can look at images. It can do visual encoding. So we can actually say, is it a chihuahua or a muffin? And actually get Spark to solve that problem for us, which is impossible to the human eye. So it's just so many things that you can actually do baked into that one engine, which is cool. I mean, it can talk to a load of stuff. So that flexible ecosystem, because we've got this whole translation of we give it some instructions and then it figures out what to do and passes that down to the bottom part. So it can mean that we can write a bit of SQL or R or Python or Scala or C# actually in the latest kind of Microsoft versions. And it'll turn that into the same thing. So it's very language agnostic, which is great. And it can plug into a ton of stuff, especially in Azure. So talking about Spark, it's just used for many, many things. It is a whole engine ecosystem of its own. So let's have a quick look at an actual bit of Spark, doing my fancy screen switching thing. So this is a quick notebook. So this is just a little bit of notebook. This is inside Databricks, but again, lots of Spark systems allow you to use Jupyter notebooks in various different ways. And I've just got a real simple bit of Python. So this is currently hooked up to a cluster. So I have a cluster that's sat here, that's running. I'm on Spark 3.1, which is just released, which is very fancy. And essentially all I'm doing is saying, I want to go and query some data. So over here, can we see that? There we go. I've just got a data lake. So this is using Azure's Data Lake Store Gen 2, but you could use an S3 Amazon bucket, all sorts of different data stores. And essentially, I've just got CSV. Super, super simple. But I've got a whole folder structure. So I've got lots of different folders of CSVs, and I could have thousands of files, millions of files, essentially a whole data ecosystem stored in my lake or many lakes. And essentially all I'm doing is saying, well, I want to make a new data frame. Data frame is essentially a flexible table construct. And I want to use a Spark data reader. So I'm saying, well, Spark, I want you to go and read something. Now, because I'm doing a CSV, I'm telling it to CSV, and actually I want it to figure out what are the column headers. Because it's a CSV, it doesn't have a data type. It doesn't have anything tied down to it. So I need to tell it actually how to figure out what that looks like. And I'm asking it to infer its schema. So it's going to sample the data slightly on read to decide what it should look like. So I can go and run that. That'll go off, read that CSV, and come back with my structure. And also tells me a little bit about it. Now, that's fine. I mean, reading a CSV is not particularly exciting. But the big, big thing for me is just how how flexible this thing is. So all this, anything that is text, anything that is in blue, anything that's being passed in as a variable, is a variable. It's entirely dynamic. So I've got this thing that's going off and reading some data, and I can just change that and say, well, actually make that customer. Instead, rerun it again, and it just runs the same script, but actually it's looking over a different data set with different settings. And I can take that data frame thing, so I've got that DF, and I can do things like down here. I'm just saying, well, actually just add in some columns. So overwrite my data frame with a new version of that data frame that has a process ID, has the name of the file I got the record from, has the current timestamp, normal lineage kind of things. It's taken that data, and I've got these things. I've got which file it came from, what the updated date was. But if I actually say, well, let's change that back, let's do that over a product instead, rerun that, and then go and kind of rerun that exact same script that I had, and now it's done the same thing, but over product. So when you talk about ETL and you get that whole idea that people are building out, every time you load a new bit of data, I have to write a new ETL package and deploy it and manage it and look after that growing pile of code. And then you go, well, actually, I'm going to write one script that does all my data cleaning, that does all my sorting of stuff. I'm just going to throw different parameters at it. Suddenly, the whole engineering aspect of looking after data becomes really, really easy. So essentially, you see a lot of things in Spark, which is that data engineering, right? It's that coming together of applying software engineering principles to data systems, but actually not having it so suddenly you can't use any of this stuff, and not having it so it's inaccessible to people, because you can just apply everything you know about data. We just take a last thing and say, like my data frame, I want to create or replace temp view. And what we can do is actually chuck it over and say, well, this is all Python. I'd actually be like to be able to just query that as a bit of SQL. So I can go in here and say, this is a SQL box. So in all the other cells, it's assuming it's Python. I'm overriding that and say, just for this bit, make it SQL. And I can now just go and select start from product. And I can write SQL. And I can go and write any SQL queries I want in it. And I can save that as an actual table. So when I'm actually playing around here, I have things that look like a database. I can have people go and explore my data and see what's going on in there, even though it's still flat files, even though it's still in this nice cheap lake, and I can turn my cluster off and I'm no longer paying for compute, but my storage is still there. And I can do this whole mix of everything. So you see this whole blend of people who are like doing data engineering by writing Python, writing Scala, writing R, people doing machine learning, again, machine learning at scale on a big distributed engine, but also people doing SQL analytics, people, again, doing database queries, doing facts and dimensions and all of that kind of stuff. It's kind of accessible because it's kind of all of those things coming together in the middle. So big fan of Spark. You might be able to tell. It's kind of what I do. So we do something like this. Controversial term, the lake house, or just basically a lake-based warehouse. Loads and loads of things going on in there. But essentially, most of the architectures that we end up building these days, it's taking a lot of the learnings from building traditional warehouses. You land your data in its rawest form, so you've got a record of what you got sent. You keep a cleaned version of the data so you can go exploring in it and do data science in it and all that kind of stuff. And then you have the curated, shaped models ready for analytics. You pre-baked a load of business logic into it. And we do similar things, except now it's just areas of a lake we do it in, rather than needing to pre-build parts of a database and rather than need to kind of, continually size databases. We just throw it in a lake because it's nice and cheap. And that used to be okay, but have a ton of compromises in it. And these days, it's a lot better. The tools are getting a lot more mature. They're allowing you to write much more sophisticated SQL in it. So that's kind of what we spend a lot of our time doing. So that's kind of looking, mentioned kind of Databricks a few times. The whole thing is it's all based on this one open source project. In the middle, you've got the Spark engine, which is more than an engine. It's a gigantic ecosystem. Got a whole load of stuff sat in there. But when if you're in Azure, then you've got Databricks in, as we mentioned. You've got this new thing, Synapse Analytics, which the guys mentioned in the questions, which that's got its own Spark tools in there. And that uses a flavor of open source Spark. So again, you can just take your open source code that maybe you wrote a bit of it in Databricks, and most of the same code will work in Synapse. And you've got a thing called HD Insight, which is a much more vanilla Hadoop instance in which you can still write Spark in. And then over the fence, if you're looking at AWS, you can use Databricks again. They're everywhere. And you've got this thing called EMR, which again I never use, which is a Spark instance as well. Same down in GCP. You've got Data CPR, I think it is, something like that. And you've got Databricks in there. So essentially, you've got Spark variants in each of the major cloud platforms. But also, you can just take the vanilla Spark project and actually plug that into your Kubernetes instance. You can run it in Docker. You can run it on a local machine. It was built to run on a set of local cheap machines. So yes, there's lots of providers. There's lots of places you can go to and get this pre-bundled premium version of Spark, pay a slight license fee and have a load of stuff in there. But there is a massive open source community, which is actually contributing into the core engine, and you can just pick it up and use it on your own. It's a little bit harder. You need to actually set up a little bit of the ecosystem and set up your drivers and your worker nodes and all of that kind of stuff. But it is there and accessible, and you can go and have a play. So it's kind of this whole continuum of a push a button, start working in it, all the way through to completely roll your own based on the open source image. There's a few, how are we doing for time? Oh, okay, we'll hurry up. So there's a few more bits and pieces that actually make up the full kind of the full package of what's going on. One of these ones super important called Delta Lake, which I hate the name because in data we always talk about, oh, I've received a Delta. I've received my change data in a Delta form. It's actually the name of a file format that people are adopting quite heavily to use in lakes. Now it's using columnar formats. So the same as the guys talking about, talking about actually taking your data, squeezing it down, it's the same idea. So when we're dealing with flat files, there's a thing called Parquet. which is columnar storage for flat files. And it does run length encoding, it's really good compression, does data file skipping, all of that great stuff. Now, Delta is this transaction log that sits around the top and it enables you to do things like have an audit trail, gather statistics on your data, do more efficient data skipping. Allows you to do a rollback of your data going, whoops, I've accidentally just completely mangled my data. I can just roll it back. I can run temporal queries and say what it used to look like. So just like loads and loads of functionality that's enabled by that. And it was built by Databricks, so there is a premium version of it, but they've open sourced it and donated it to the Linux Foundation. So you can actually go and contribute to it and actually sort of commit changes to it and help with bugs and actually get working with that as an open source file format. And again, it is really, really cool. It's also really simple in terms of how it works. So if I have a look at it, I've got my data sitting around in a lake. I've got a load of Parquet files, these nice optimized compressed bits of data. And then all it is it just adds a transaction log. So you get a little JSON file that when you open it up just describes what's inside there going, I'm currently made up of these Parquet files. And if someone updates it, it just creates new Parquet files and then transaction log says, actually now look at these ones instead. And just that simple mechanism gives you a whole world of functionality that makes it behave a little bit like a proper relational database, but you're on this massively scalable cluster on top of a super cheap lake. So it's loads and loads of stuff going on inside it. On the other side, the other open sourced element is a thing called ML Flow. And now that's much more on the machine learning side. It's machine learning flow. And that is a whole platform for doing things like experimentation tracking. So you can do things like run an ML package with different parameters, different sets of data, and actually it'll track the results. So you can say, well, actually, which one performed better? Which one is actually, which of the different sets should I go back and use? You can kind of just do auditability of machine learning, which as we look at things like bias and fairness in AI, becomes incredibly important. So there's loads of things that are around ML Flow, which are just vital for the whole machine learning elements of things. So super, super, super important. And again, open sourced, donated to the Linux Foundation, can be contributed to. So as a final thing, I realize we're at the end of the time. There's various different parts that you can actually get involved if you wanted to. So obviously there are those core bits of the open source projects themselves. So the Spark engine is fairly intimidating because it's absolutely massive, but you can go in there and actually raise issues. You can kind of do a pull request, start working on parts. It is an entirely open sourced system. There's also Delta Lake and ML Flow, as we mentioned. They are open source and you can go and contribute, you can work with them. But one of the bigger things and the easier ways to get involved is actually on the package side of things. It's connecting to Python, R, Maven for Scala. Because it is using these kind of very, very open languages, there's a whole massive ecosystem of people actually going, oh, I've got a really good idea. I'm just going to write a little Python package that will use PySpark, put that into PyPy, and then that actually sort of pull things right down. And it's just super, super easy to go and work with a lot of that stuff. So writing your own package or contributing to open source packages that are actually out there in one of the public repositories really easy to get involved. And then finally, obviously, there's the huge community around it. So there's tons and tons of documentation. There's tons of people asking questions because it's such a growing thing. It's got such a mass of, movement behind it that loads of people are trying it and having problems and getting involved. So helping people out on the forums, going to the forums for help, sharing YouTube as you find various different things out. There's just lots and lots of different ways in the wider community to help people actually getting involved in Spark and working with it. So all the way through from helping build the actual thing, building the ecosystem and libraries around it, to just helping out in the community. It's just a massive, massive community these days. So lots and lots of stuff you can go and get involved with. There we go. That was blasting through lots and lots of things. Again, feel free to ping any Sparky questions at me. Do run a YouTube channel where I talk about all things Spark and Databricks and Synapse and all that kind of stuff. I am largely on the Microsoft side of things. But generally, most of the features, most of the things that we talk about in terms of Spark are part of the open sourced engine. So it's as innately transferable as it is. Cool. Okay. Do we have any questions?
Yes. So, can you pull up the issues and help find good beginners issues or good first contribution issues?
It's quite
As
an
in, can I do it right now? I do not have any of it open or have any of the links to hand. So, not
Can you
not
pull them
immediately.
up, like, out of your head?
Were you able to send in your own contribution already on the open source part?
So what I can do is I'll pull out a few from the links and I'll put it out on Twitter later. So I'll have a bit of a dig, find us some areas and go, here's some areas you can get involved. Probably the easiest. Certainly my contributions, I don't have any contributions in the main open source one. So I just write packages. So I write bits of Python. And most of what I do is actually just use other people's packages and then educate. It's my main thing. So my majority of stuff is forums, it's documentation, it's doing YouTube, and then it's writing packages on top of things that we use to build out the ecosystem. That's my main bit. So I don't have any open source Spark contributions I can show you, I'm afraid.
But let's say sharing with the community is also open source. It's free and people can view it. So that's also a good thing.
I do a horrendous amount of YouTube. So if you want to know about things, just go watch videos. Fine.
Well, we know that education, documentation, and marketing are very much important parts of doing open source altogether. Maybe we can pull up the link for the YouTube thingy. I'm asking.
Yes,
Nick.
can do.
There you go.
Grab that.
See, there. And we totally recommend everybody to check that out. Right?
Indeed. Cool. How would you...
Do we have any other questions?
There's not really questions coming in at the moment, but how would you... Where do you start if you want to learn Spark?
Yeah, I mean, so it can be super intimidating, right? Because you've got this just gigantic pile of functions and people have been working it for 10 years.
First,
Sorry?
Do you need to start learning Python first or SQL, or is it not really needed? Or
when you get to the engineering part, if you're trying to do the thing that I showed where you're building one script and using it many, many, many times, you can do that in R, Scala, or Python. It's essentially pick one, choose your favorite. In terms of if you're just starting out, if you don't do a lot of programming, Python is a hell of a lot easier to learn than everything else. So Python is quite accessible and quite nice to get started with. Scala, functional programming, it's a lot more robust. It's a lot more kind of deep in terms of how you can build that. But it's a little bit less accessible, a little bit harder to write. So we find most people kind of get started with Spark writing a little mix of a bit of Python and a bit of SQL, and then you're pretty good to start. There are some places you can go for things like free trials. So one of the things I will drop is Databricks do a community edition. So you can kind of just spin up a notebook and have a bit of a play without paying anything, which is the nice thing. So let me just grab that. I'll pop that link over here. And that just allows you to have a bit of a play. So you can go and do that, spin up a notebook, write some Spark on basically just a little single engine. And that's kind of running, I think, on their AWS version. So kind of when I first did it, I think kind of you guys have done things like Advent of Code, right? Kind of where you have all these kind of code katas, all these challenges that you have to write. Essentially, I normally just grab Advent of Code or something like that, and then just try, can I do this challenge in a Python notebook using a single Spark node? And it's a little bit, kind of sledgehammer to crack a nut, but it's a good way to kind of just try and challenge yourself and learn how it works and try and get the foibles and quirks of it. And kind of, that's how I get a lot of people to start learning it.
Okay, cool. If there's one thing that you would like to share with the public, like never do this with Spark, what would it be?
For me, I think it's the opposite. I think for me, there's lots of people who first come from the SQL community who they're always like, never use cursors, never do things in a loop, never do iterators. And you have these things like built into your mind. And that's not a problem in Spark, weirdly, because Spark is a thing called a lazy executor. So when you're talking, I got that data frame up and I said, just spin. kind of just, you can go in a loop and then change that and change that and change that and change that and change that. And all those instructions, all those things that you're telling it to do, don't actually do anything. All it's kind of basically building up a list of instructions in its mind. And it's only when you say, now show me the data, or now write the data, and you do a thing called an action, that it goes back and turns that into an execution plan. So you get a lot of people that try and write things in horrendously complicated ways because they're thinking in SQL. Whereas actually you can do like bits of programming and it's not as bad as it seems. And that seems to trip a lot of people up when they're first starting, because you think of it in SQL not as this thing that's just lining up a load of commands and then figuring out the smartest way to do things. It's crazy.
So actually you can make it more readable than SQL.
Yeah, much more. I mean, certainly in SQL, if you try and write dynamic SQL and you end up with just a whole one mash of a thing and you can't quite see what it does, it's much, much easier to actually read because you can just write some nice instructions.
Try to debug that.
Yeah. So basically, your advice is to unlearn SQL, watch hours of your YouTube channel, probably.
But of course.
And rewire your brain. No, but it is quite. Don't unlearn SQL. Neil says don't unlearn SQL. Well,
I would never say not to learn SQL. SQL is awesome, and I spend a lot of my time writing SQL. It's just don't let the lessons of the SQL past implement your parallelism thinking.
Maybe we can have some 15 minutes and you and Niels just go figure this out together, what the most acceptable answer is.